Hi, it's me Base again. This video will be a walkthrough on all the interesting and hard questions on the paper 3 statistic part, where I handpicked the questions from the year 2018 to the year 2024. So the questions will be split according to the topics following the syllabus. So there will be data presentation and interpretation, probability, statistical distribution, and hypothesis testing. Please help support me by like or subscribe, or do both if you love me. See you in there. Okay, let's look at the first topic, data presentation and interpretation. Alright, so let's see the first question. This is from October 2021. Staff is studying the large data set for September 2015. He codes the variable daily mean pressure x using the formula y equals x minus 1010. The data for all 30 days from Hearn are summarized by that. A, state the units of the variable x. Now, this is why you should be familiar with the variables and units from the large data set. For the daily mean pressure should be hectopascal, right? Okay, so that's the answer there. So you should just be familiar with it. B, find the daily mean pressure for these 30 days. Alright, so that's easy. We're just gonna do x bar equals delta x over n because we're given it. Now we're just gonna find the y bar because we're given the data for y. But if we find y bar first, we can use the coding equation to convert that back to the x bar. So y bar will just be sigma y over n. And that is just 214 divided by, well, the number of data is 30. So 30 there. Okay, so that's 214 divided by 30. Gives me 7.133 ... Now because we want the x bar, right? So x bar will just be, if you rearrange, make x the subject for this coding equation, you're going to get y bar plus, right? So that also works for the mean. Yeah, the coding equation also works for the mean, right? So that's going to be 7.133 ... plus 1010. So that works out to be 1017 hectopascal, yeah, for the 30 days. Okay, and that's for B. C, find the standard deviation of the daily mean pressure for these 30 days. Standard deviation is the square root of variance, where the variance is just the square root. Yeah, I'm just going to find for the y first. So that's going to be sigma y squared, right, divided by n minus y bar squared. Yeah, and then again we can use the coding to convert that back to the SD for the x, and I'm going to tell you how that. And then well, we just have to calculate that first. So 5912 divided by 30, yeah, minus, we already got y bar above, so that's just that squared, right? So we're going to use the calculator for that. Square root, the first one is a fraction, 5912, yeah, divided by 30. And then we minus 7.13333 squared. Okay, so that's 12.091. Okay, 12.091. I'm just going to put as that first. Now, because the coding equation is this, right? Well, for the mean, right, if we get x bar, we got to minus it by 1010 to get y bar. That's right. But for this one, because the coefficient of x is 1, so that means the SD of y will also be 1 times SD of x as well. If there was a number here, let's say 5, then the SD of y would be 5 times the SD of x. Now note that this is going to be different for variance, because for variance it's still relatable. So y would be the coefficient of x here. Let's say a is going to be a squared, the variance of x. Yeah. So in this case we're doing standard deviation and the coefficient is 1. So we're just going to say that then the standard deviation of x is just the standard deviation of y is just the same number there, right? That is the standard deviation of the daily mean pressure for 30 days. And we're going to put hectopascal as well. So that's for C. Part D, probably more interesting. Staff knows that in the UK, winds circulate in the clockwise direction around a region of high pressure and in an anti-clockwise direction around a region of low pressure. The table gives daily mean pressure for 3 locations from the large dataset on 26th of September 2015. Location, Heathrow, Herne, Lucas, daily mean pressure, blah, blah, blah. And now we note that Heathrow, or somewhere near it, has the highest pressure here, although not a lot higher, but it is the highest pressure. And we'll note that. And now it's leaving the cardinal wind direction for us to fill in. The cardinal wind direction for these locations are in random order west, northeast, and east. You may assume that these 3 locations were under a single region of pressure. Right, so that's a good hint there. D, using your knowledge of large dataset, place each of these cardinal wind directions in the correct location in the table. Give a reason for your answer. Right, okay, so we note that because Heathrow is the highest pressure, yeah? So Heathrow, highest pressure, yeah, highest pressure, although not a lot higher, but still highest. So let me just draw the UK, yeah? And I'm not good at this, but I'm going to try my best. Something like that, maybe. Okay, maybe like this. And you should be familiar with all the major cities in the LDS. And these are the 3 main ones. I mean, there are also Camborne and others, yeah? So Heathrow is around here, yeah? Around the southeast of the UK. Yeah, maybe more to the east, near London. And this is the Herne. Herne is around here. And Lucas is a lot like to the north, right? So it's around, maybe around here. Yeah. So that's L, that's Heathrow, and that's Herne. Okay. Right? Around there. And actually, Lucas is probably more to the right, but it's around somewhere to the north, right? So when we got the highest pressure, Heathrow, so we will use Heathrow as the reference. Because Heathrow is the highest pressure, so the wind direction will be what? Clockwise, right? So it is clockwise around or near Heathrow. Right? So it's something like this, maybe. Yeah? So I'm just going to use a different color, so it's like this. Okay? Or we can do larger than that, so like that. Yeah, okay? Now, this is important now, because when you consider the wind direction under the effect of a single region of pressure, this is the very key. And this is actually not very accurate to do, but because we are told to do that, yeah? So the effect of all the locations here from these cities or these areas, regions, will be assumed to come from this single high pressure wind direction, which is what I drew there, the clockwise, right? The high pressure, okay? So like for example, if we look at Lucas, which is up to the north, so the wind direction of the high pressure here will be going to the right relative to the area in Lucas. That's the best we can do. So it will be going to the right, and that is coming from the west. Because look, the wind direction we are using here will be the direction from where the wind comes from. Because it seems to have come from the left, right? Near Lucas there. So we're going to fill in the west, right? West for Lucas here. Okay, so in the table, you just put a W in under Lucas there, because it's going to the left. Okay, now let's have a look at another city here under the effect of Heathrow, high pressure there, Herne. Well, look, Herne is like, okay, if you go around, let's say go around from there, high pressure, and then when it's arriving at Herne, it's probably about to go that direction. I mean, look, if Herne was just below Heathrow like that, just like almost directly to the south like that, well, it would be from the east, right? Just the opposite to Lucas there from the west. But this is not exactly to the south. It's more to the southwest, right? So when it's more to this direction, then the wind should have come from this direction here, which is the northeast. We only have one here, northeast. That makes sense, right? Because north is up and east is to the right. So there you go. Because Hearn is not directly to the south. And that is, the wind direction for the Hearn. So we do northeast. And now Heathrow itself, right? The best we can do here is the east. And that makes sense. So the best kind of like prediction here that we can say about the location of this wind origin is probably somewhere to the north of Heathrow. So that's why Heathrow will have the wind going from the east, right? Or right to left here. So the wind will be coming from the east, passing Heathrow. So we do east for Heathrow itself. Yeah, and you got all the answers there. So we have to say that, okay, it's clockwise near the high wind direction, high pressure. And then, so we write down the direction of the cardinal wind. So Heathrow, we say east, and then Lucas, we say west, and then Hearn, we say northeast. And that's it. Yeah, and I already explained the logic there to determine all the wind directions here. All right? Okay, so that's it for this one. Next one, June 2024. And this one is a very good one. And I already walked through the question here in the other video. I already put the link in the description, so you can check that out. And also don't forget to come back here after you're done with that one. Let's look at the next topic, probability. Okay, this one can be tricky for people here to crack, because you probably have to visualize the problem a bit, and maybe I would like to say that you should try to be immersed into the problem to solve it. Like, imagine if you were having this same problem or situation, like what can be the outcomes, right? Okay, let's go. So the first one we should look at is June 2023. Yeah, Tisam is playing a game. She uses a ball, a cup, and a spinner. A random variable x represents the number of spinner lands on when it is spun. The probability distribution of x is given in the following table, right? So we get the table here, blah blah blah. Okay, so this is chosen because look at the level of complexity. You don't know anything about the probability, okay, at least for the time being. And then later you got these conditional probabilities. And then you got to use all the information here. So basically it just combines the concept of statistics with algebra, right? So that's why it's a little more tricky there. Okay, part A. So after you might have read all the information here, we're going to solve part A, show that C equals 8 over 5B. All right. So at least you just glance the table. You know that this is a probability distribution or sampling distribution, whatever you want to call it. We should know that when we sum up the probabilities, the probability values there, the Px equals x, we should get 1. That's the very least thing we can do whenever we see this, right? No matter what information they give you, this is the law. They sum up to 1, okay? And then, of course, we should look into the details here. The model, to model this game, Tisam assumes that, okay, here we got the conditional probability, right? So if you look at the conditional probability that they give you here, this is saying that P S intersect, I'm just going to write according to the definition of probability, the conditional probability. This is Bayes' theorem, but you don't even need to know his name. Intersect that x equals x, right? And then divided by P of x equals x, yeah? So this is just basically saying it's just one of those, like x can be anything, x equals x, and s. And s is what? The event S represents the event that Tisam successfully throws the ball into the cup. This is saying to you the probability of the ball getting into the cup when he stands at a particular distance x centimeters away from the cup, right? So basically, if x is 20, this is just k over 20. If x is 50, this is k over 50, yeah? And this is the condition there, okay? And then we get another one, P of S intersect, that should be the same. Aha. So if we consider this equation we have right here, right, with the next line of information, yeah? So if we make this the subject, right, we're going to get k over x times p of x equals x. And it is saying that this thing, p of s intersect x equals x, or to say in words, this is the probability of Tisam having to stand at a particular distance x and successfully throw the ball into the cup, right, is equal to this thing. And it is saying that no matter what x value is, this whole thing, or actually this thing, is a constant. So because in part A we need to show for C and B, and they come from C is 80 here and B is 50. So let's have a look at these two cases, right? So if we, let's say x is equal to 50, yeah? So P of x equals 50 is just B. And then x equals 80, P of x equals 80 is C. Let's then compute this expression here. So this is just k over x is 50 and times b. Because this thing is already this thing, right? And it should be constant, so it's equal to this thing, but for the other case here, which is k over 80 times c. Yeah, because look, what we have here is just from this, which is this, which is to be the same for the other case. So that's why I got this equation. I hope you understand. If you don't, maybe try, wind it back and try listen to that again. Now, yeah, obviously k cancel, right? So we can get that equation there. So if we make c the subject, we get 8 over 5b as required. Yeah, so that's it. Part B. Find the probability distribution of x. Okay, so that is just to find the whole thing in this table, right? Just the whole thing. So basically we need to solve. Now, because part A is a good hint for you to guide you what to do next, because you already did C in terms of B, right? So you got here already 8 over 5b, and here you have b, right? So this is for the 50, this is for the 80. So we should do the same for the other two. Okay? So look at the relationship between the numbers here. If this is 80, you do 8 over 5. Yeah? It's just dividing 50 into 80 there. So if we do between 20 and 80, I'm going to make A in terms of B basically. So I'm going to get, so it's 20 over 50 B, right? So it's going to be 2 over 5b. And the other one would just be what? So that's going to be 100. This one will be 100 over 50, right? So that's 2b as well. Yeah, between D and B. So these will add up to 1, don't they? Right? So that will add up. Sorry, this is B as well. Equals 1. And we just solve for that, right? So 2 over 5 plus 8 over 5 plus 2, what's the other one? Plus 1, yeah? Was it? 2 over 5, 8 over 5. That's 5. So 5b equals 1, b equals 1 over 5. 1 over 5, sorry. Right? So that means the distribution is now going to be, so for x equals 20 here, it's going to be 2 over 5 times 1 over 5. It's going to be 2 over 25. The next one is 50. So just 1 over 5 there. And the next one is 80, right? So 8 over 5 times 1 over 5 is 8 over 25. And the next one, 100. Yeah. B, which is 2 over 5. And of course, if you add them up, you should get 1. Yeah, so 2 plus 5, 7, 7 plus 8 is 15, and then, yeah, plus 10. You get 1. All right, so that is the part B done. Part C. Nav tries a large number of times to throw the ball into the cup from a distance, 100 centimeters. He successfully gets the ball into the cup 30% of the time. State giving a reason why Tisam's model of this game is not suitable to describe Nav playing the game for all values of x, right? It's getting quite some more real-world problem, if you know what I mean. Because when you have a statistical model and you wish to use it into other cases, Nav's trying to just throw the ball from a fixed distance 100 centimeters. And when we want to apply Tisam's model here, in which when you have a distance x and then you're going to throw the ball from that distance, yeah, it is the same here as P of S given x equals x, right? That's still the same thing, and that was given earlier to be k over x, remember? And because Tisam's model is saying that k should be a constant, and Nav here tries a very large number of times to throw the ball from just one single distance, 100 centimeters. So we're going to try use that for x equals 100. Let's see what Nav is trying to get here. So the probability is 30%, and that is 0.3. So it's just basically this whole thing being 0.3. But if we try equate that to k over x and x being 100, we obtain k equals 30 here. Okay, and to follow Tisam's model, k needs to be a fixed value, right? So we're going to try for other values. So I'm going to say here x equals 20, 50, and 80. We're going to try for all other values, right? The probability of then s given that x equals x will be what? We already got the value of k, right? So we're going to try do for all of them. We already know for the 100 it's going to be 0.3 here if we use that formula, right? And we now get k to be 30, so we're going to do 30 divided by x. Let's do from the right, yeah? So 30 divided by that, 30 divided by that, and 30 divided by that. Well, if you check through this table, do you see anything wrong with this? Right? There are probably a couple of things that can go wrong. Yeah? The very first one and the most obvious one is the probability of the, x being 20 centimeters here, because it's greater than 1. So that is almost saying that about 100% and 150%, which is kind of like not possible, Nav will throw the ball into the cup for x equals 20 centimeters, which is kind of like theoretically not possible. And for what's worth, I mean, although this, let's say this wasn't that bad. Let's say this was, say, I don't know, 10 over 20. Let's say that was 10. And if you add these up, you're not going to get 1 either, right? Yeah, you're not going to get 1 either. But this is the most obvious thing to say, right, for the reason that. So P of S x equals x is going to be 30 over 20, which is greater than 1, which is not possible for probability theory. Okay, and that's probably how you answer that one. Now let's have a look at the next probability question on June 2018, right? And this is from question 3. In an experiment, a group of children each repeatedly throw a dart at the target. For each child, the random variable h represents the number of times the dart hits the target in the first 10 throws. Peter models h as binomial distribution 10, 0.1. So 10 is the number of trials, which should be 10. And 0.1 here is the probability of 10% of each one hitting the target, right? And part A, state 2 assumptions Peter needs to make to use her model. So this is kind of like on the topic that overlaps with the statistical distribution, because this is binomial here. But you know, the later part, like part C, D, E, and F, those are interesting probability questions. So we're just going to do the easy ones first here, A and B. So A, state 2 assumptions Peter needs to make to use her model, right? So it's just the core assumptions of binomial distribution, right? Which are, or the events are independent, but we need to write in context here. So each throw is independent from one another. So that is to say that the current throw is not going to affect the next throw, right? But in reality, they might, you know, like when you throw the first dart and then you aim like that, and then it's like a little off the target. So the next throw you might do better, maybe. I mean, if you are professional enough, yeah, and other factors too. So, but that's the assumption here. So there you go. So the first one is that the trials are independent. The next one is to say that the probability of hitting the target is constant at 10%. So there are just two outcomes: hitting the target or not hitting the target. Yeah? Okay, so the probability of each dart hitting the target is the same as 10%. Yeah, so those are the two assumptions there. And now part B, using Peter's model, find P of H greater than or equal to 4, right? So probability in a binomial distribution, right? You can use the calculator. So in a graphing calculator, there should be binomial CD, right? So you need to put the X value, the N, and the P. But in this case, we want probability of greater than equal 4, so you need to change that to 1 minus P of H less than equal 3. Don't forget, this is a discrete distribution, so we can't just go less than equal 4 there. We just gotta do one less, because if we did 4 here, that doesn't make sense, because if we did 4, it would be right for greater than 4 only, right? But this one is including 4, so we can't subtract 4 out. We gotta subtract 3 instead. Okay, so I'm gonna use my Desmos calculator actually, because I don't have a graphing calculator, which should do the same thing. So I'm just gonna do function, and then I go to probability distribution, and I have binomial distribution here. So I need to put trials, which is 10, and probability of success, which is 0.1, isn't it? Yeah. Okay. And then cumulative probability. Well, I'm going to do from 0, because I'm going to be fair to you guys here, because you guys should do from 0 to 3 here. Yeah. So that's going to be 1 minus 0.98. Yeah. 720. Okay. And then I'm going to use a calculator to calculate that. 1 minus 0.98720. So that is the answer to that. All right. And next part C. For each child, the random variable f represents the number of throws on which the dart first hits the target. Okay, using Peter's assumption about this experiment, find Pf equals 5. Okay, so you got to keep throwing until you hit the target. If you don't hit the target, you keep going, right? And f equals 5 here means that you will have thrown 4 times, and the 5th time it hits the target, right? You got to make that clear to you first. You got to understand that first. So P of f equals 5 here means that this child will miss 4 times and get it the 5th time. Yeah. So missing is the probability of missing target is 0.9. So we got to do 0.9 to the 4 because we missed 4 times. So you got to, it's a compound probability. So you miss, and then you get it. Okay. And then you get it is 0.1. Okay. On the last throw. Yeah. And then that's it. So we just calculate the probability of that, 0.9 to the power of 4 times 0.1. Okay, so that's 0.0656 as the probability there. That's not bad. And now the next one is the interesting bit. Yeah, Thomas assumes that in this experiment, no child will need more than 10 throws for the dart to hit the target for the first time. He models PF equals N as this, right? And alpha is a constant to be found in part D, right? So, well, like for example, the maximum number of N should be 10, right? Yeah. And this is 4 marks. So if we want to find the value of alpha, it seems like, yeah, we got to use the golden rule of probabilities here, which in one event, all the cases add up to 1, right? So the P of F equal 1 equals 0 is not possible, right? So if we expand all the probability distribution here, F is going to go from being 1, right? Because you stop when you get it. So if you don't throw, you don't stop. So you got to throw 1 time. And if you're lucky, you're going to get it the first time. So the minimum value of N is 1, right? And the maximum value of N would be 10 because he assumes that they need more than 10 throws, right? Okay, so we're just going to do a table actually. So we're going to do, so I'm just going to go like N and then 1, 2, 3, 4, 5, 6, 7, 8. Amount of space, 9, 10, okay? And then P of F equals N. Okay, so we're going to do quickly here for N equals 1. If you plug 1 in here, this is going to go to 0, so we get 0.01 here. If N equals 2, yeah. So if N equals 2, this is going to go 0.01 times alpha. Sorry, plus alpha, right? Okay, and do you see the pattern? If N equals 3, you're going to have 2 alpha, right? So this is 0.01 plus 2 alpha. And if you keep going, yeah, at 10, you're going to have 0.01, this is at 10, plus 9 alpha, right? And this is actually arithmetic sequence, isn't it? Arithmetic sequence. Where you can just, you see the pattern here, they add by alpha. So alpha is the common difference. Right? So, I mean, if you want to do this quickly, you just, get the pattern there and use the arithmetic sequence formula. So we want to find the sum. We want to find the sum of all probability here, right? Should be F equals N there, should be equal to 1. But the sum is just the first term, yeah? So we're going to use Sn equals A plus, sorry, it's just, well, we can do the first term plus the last term divided by 2 multiply n. That will also work because we seem to know everything here. So the first term is 0.01. The last term is 0.01 plus 9 alpha divided by 2 times n, which is 10. There are 10 terms, right? Yeah, 10 cases, 1 to 10, equal 1. And that is just to solve for alpha, yeah? So we cancel there. So this is on the left side, we have 0.02 plus 9 alpha equals 5 dividing into 1. We get 1 over 5 there. 9 alpha will be equal to, well, not 1 over 5 is 0.2. So 0.2 minus 0.02 is 0.18. Yeah, and alpha is just 0.18 divided by 9, which is 0.02. Right? And that's alpha there. Okay, in part D. Part E, using Thomas's model, find PF equals 5. Okay, so Thomas's model is just still this, and then we want to find PF equals 5. Well, that's not hard. I think we found it, right? Yeah. So that is just, I mean, we already found the alpha here. So P of f equals 5 according to Thomas's model would be 0.01 plus 5 minus 1. Alpha is 0.02 as we solved it earlier. So that's going to be what? 4 times 0.02 is 0.08. 0.08 plus 0.01 is 0.09, right? And that's it. Okay? And part F, explain how Peters and Thomas's models differ in describing the probability that a dot hits the target in this experiment. So if we compare, because look, we have done P of f equals 5 for both according to Peters' model and Thomas's model, right? So looking back to Peters' model, P of f equals 5, it was what? Part C, right? This is 0.0656, yeah? So if we only do P of f equals 5 according to Peters' model, it's going to be 0.0656, isn't it? Yeah. But versus P of f equals 5 according to Thomas' model is 0.09. Do you see that Thomas's 1 is greater than Peters' 1? Okay. Now, what was the nature of Peters' assumption again? Well, each throw was independent of one another. Yeah. So because each throw has a fixed probability value of about 10%. So no matter how many times you have thrown, you get the same chance of hitting it. Somewhat that is, as I mentioned earlier, that might not be true for reality, because as you play more, you get better, hopefully. Well, for normal people. But yeah, and that may be something a little off for Peters' model. That's why here we see that Thomas's model is a little different, because for the same kind of situation, we have probability of a different value, which is slightly higher. So this is suggesting that, I mean, if you try, I believe that if you try calculate P of f equals 6 for both cases, you're going to see a larger difference. In fact, we should try, right? So if we try for Peters and Thomas's for P of f equals 6, yeah, for Peter as well. So that would be you're going to miss 5 times, and you're going to get it the 6th time. So 0.9 to the power of 5 times 0.1. All right, let's note that down. 0.059049. You see the number is now smaller. But if we do, according to Thomas's model, is 0.01 plus n is now 6. Yeah. So that would be 5 times alpha, which is 0.02, right? Yeah. So that's going to be what? 0.11. You see, that's even higher than before. It is contradicting to Peters' model here. It's like the opposite behavior. For Thomas's model, as you throw more, the probability of getting the next one is more. Because let's say you have done 5 throws and none of them hit the target. So the 6th throw, you will get a better chance of getting the target. That's for Thomas's model. But for Peters here, maybe not. You will do worse. You get a smaller probability of hitting the target, right? So that's the difference here, and we will have to comment on that, okay, for part F. So yeah, so for Peters, the probability of hitting a target is the same for each throw. We are talking about each throw here, okay? Meaning that the probability of hitting the target the next time after all no hits will be smaller. Yeah, it will be smaller the more you have done no hits, the next hit, the probability will be smaller. That's bad, right? If you think about the reality. Okay, so like you don't improve at all. That's what it's suggesting there. But for Thomas's, yeah, the probability of hitting the next time increases, yeah, increases with the number of times each child has missed. Okay, there you go there. The next one is again June 2024, and again please check out that video. I already explained everything in there and it should be fine. I think I did fine for this one. Okay, so let's go to the next topic, statistical distribution. Okay, so stat distribution. So basically it's just binomial or normal distribution and then solving a problem. Take October 2021 question 5, right? Okay, so the heights of females from a country are normally distributed with the mean of that and the standard deviation of that. Given that 1% of females from this country are shorter than k centimeters. A, find the value of k. Okay, so if I would like to almost every time draw the bell curve when solving normal distributed problem here. So you have a bell curve, right? We call it a bell curve. And then 1% is like to the left. Yeah, 1% of the females. So it's like the lowest 1%. Shorter than k centimeter here. So if you take the area of this bit, it's going to be just 0.01. The probability is 0.01. Okay? And the mean is in the middle, 166.5, and sigma. So if we write down the model, it's n, and then 166.5, and then this is 6.1 squared. Have to be like that. So let's say x modeled as that. Okay, so this is not too bad. We're just going to do 1% there and find the value of k. Now, 1% would require that you need to know, one, how to use the calculator to do the inverse CD. Yeah, inverse normal, sorry. So you plug in the area, it's going to say area to you. I don't have the calculator here. So you should be able to go to mode and distribution and then do inverse normal. Then you plug in the area of 0.01. Yeah, the mean is for the Z bell curve, the mean is 0 and the standard deviation is 1. You're going to get the Z value as an output. All right, but I'm going to use a table here. So let me just get the table. Because we have a table here. For those of you whose calculators are not that advanced, I mean, they should all be equally advanced, but you can also check the table here, which is the percentage point table. It's the small one here. So there is the value where the probability is 0.01, and that is the Z value. It's just that this 0.01 is to the right. So it's the max, like the highest 1%. So it's actually this bit here, that 1%. But because we want the lowest 1%, we just put a minus sign to the Z value there. Okay, so the Z value, we just say that the probability of Z less than 0.01 will just be minus 2.3263, just for the working mark there. Okay, and let's get back to the question, right? And then we want to use this Z value to find the value of k. So this equation is required, right? You need to memorize this one. Z equals x minus mu over sigma. All right, so minus 2.3263 equals x is the k because it's the value of that particular point there, minus mu over sigma 6.1, and then we just solve for k. Yeah, so k equals 6.1 times minus 2.3263 plus 166.5. Yeah, calculator. 6.1 times minus 2.3263 plus 166.5. Okay, so that's 152.31 1, 0. I'm just going to leave it at that. Okay, that's the value of k there. Part B. Find the proportion of females from this country with heights between 150 and 175. This is 1 mark because you can just use the calculator. Okay, and you should use it. So now this time you're going to go to normal CD, right? And there will be lower and upper. So you put lower as 150 and upper as 175. And then the mean would be 166.5, and then the standard deviation is 6.1. And see what you get. But because I don't have that calculator, I'm just going to use a brain and the data here. All right. So basically, that is just required that you find this thing, yeah, in this inequality, right? But that is just equal to P of 175, sorry, x less than 175 minus P of x less than 150. Okay? So that is just P of z less than 170 minus 166.5 over 1.6, and then minus z less than 150 minus 166.5 divided by 6.1. Okay, so I'm just going to calculate those two z value. I mean, you can just hang around here to see how I do it without using that function of the calculator. Otherwise, you can just go to the next bit. It's fine as well. So that would be z of 1.3934, and the other one would just be a negative. There you go. Okay, so this is z of minus 2.7049. Okay. So is P of z less than that, and P of z less than that. Okay. I need to do, yeah, I guess I have it in my calculator here. Don't worry. Statistical distribution. And then this is, yeah, it's going to be this one. Yeah, it's going to be the probability there. Okay, so it's 1.3934. Yeah, that makes sense. Okay, 0.91825. And the other one, just going to change that to a negative 2.7049. Yeah, I think that makes sense. Okay, so go to the normal mode, and then we do 0.91825 minus 0.00346162. So that's going to give me the probability value there. Just going to leave it as maybe 3 significant figures. Yeah, so that's it. That's the value. Okay, part C. All right. A female from this country is chosen at random from those who with heights between 150 centimeters and 175 centimeters. Find the probability that her height is more than 160. Okay, now because it is chosen from this range of height, so this is again conditional probability, and that's why I picked this one, because there is this condition here you need to know. So it is basically P of x equals 160, yeah, given that is in the range of 150 to 175 here. So that's how you write the condition there. So P of 160, sorry, more than, this has to be more than 160, right? So if you draw this out, right, you have to pick between 150 and 175, and maybe 160 is around here. So let's say the probability of the height between 150 and 175 is this line. Let's say that is representing the quantity of probability then. But you are finding more than 160, right? More than 160. So it's going to be this quantity here. But it should be also within or less than 175. Okay, so you are finding this quantity over this quantity, which will give you the probability. So basically we are finding the probability in between 160 and 175, and this is already what we got earlier, right? Yeah, so we just need to find this one. And again, you can just use the calculator here to find this one, but after you use the calculator to find that, you will see that it is just 0.774947 ... Yeah, and the previous one for 150 to 175, I'm just going to take the value from the previous question there, which is 0.915. Okay, so this will be, you do the math there. I'm just gonna leave at that, and then yeah, so this will give me 0.846 or 0.847. I'm gonna leave at that. So that's the answer for this part. Okay, part D. The height of females from different countries are normally distributed with the standard deviation of 7.4 now. Mia believes that the mean height of females from this country is less than 166.5. Mia takes a random sample of 50 females from this country and finds the mean of her sample to be 164.6. Alright, so this is about the distribution of the mean of sample, right? So let me write that down first. Normally in binomial distribution, in normal distribution, we would write the statistical model like this, right? Yeah. And that is for the population. But when you take sample from this population, we're going to write it as this instead. Yeah. So we are doing a hypothesis testing to see that whether this sample mean will indicate any significant change of the actual mean from the population. Yeah. So we do this, and that's going to still be the new mean, like still the mean. So we are assuming the same mean here, but the standard deviation will be and the variance will be sigma squared over n. Yeah, and this n should be a little n maybe, because the big N is already for normal distribution. Okay, so we are testing that. All right, so that means if we want to write hypotheses, carry out a suitable test to assess Mia's belief, you should state your hypothesis clearly. Use 5% significant level. So I'm going to write H naught. Well, it's going to be mean, still the same value there, because it was the assumption early that the mean for the country is 166.5. All right. But Mia believes that it's not that, it's less than that. So this is one tail test, and H1 is just mean is less than 166.5. Now don't get confused with the 164.6, because that is just the mean from the sample. You are not assuming anything about that. You are just testing whether that value will indicate some evidence that the mean of 166.5 here will actually change, So it's like, if you think about the reality here, you are testing the sample and it shows you that the mean is 164.5, and you are thinking, whether that will suggest any change from the actual mean, right? And we're going to test that. So we're just going to calculate the probability, because this is less than, so it's the left tail here. We're going to calculate the probability of x, x bar here, less than 164.5, and see whether that is less than 5% or not, right? But to do that, you're going to need to use mu of 166.5 and sigma of square root, it's not square root, so, well, it's a square root of the same sigma there, the sigma of the population, the previous one. I'm just going to say sigma sample here, which is the sigma we're going to use. And this is the sigma of the population divided by n, which is the number of samples. And that would be, well, sigma of the population is 7.4. This is normally distributed with standard deviation 7.4. And then we square this, and then the number of samples would be 50. Now let me just get that value by using a calculator first. So square root of 7.4 squared divided by 50. Because I'm going to plug this value into a Desmos calculator later on, I'm going to need a more precise value there. And then, yeah, we're going to find the probability of this, right? Well, actually, the number here should be right. 164.6, right? Not 0.5. All right. Okay. And then let's see. So I'm going to have my Desmos calculator, this one. And then you go to normal distribution, right? And then you put down the mean, 166.5. And then the standard deviation, not the variance, 1.046518. And then toggle down here, cumulative probability. We want the left tail because we want the area from that 164.6 to the left. Okay, and then we calculate the probability, which is the area here. We put 164.6, right? And that's going to give you the value, which is 0.0347. I'm going to stop there maybe. And we know that this is less than the level of significance. So we reject H0, yeah? And this is saying also enough evidence to suggest that the mean height is less than 166.5. Therefore, Mears belief, right? Because at the end we want to assess mere belief here, right? That's the objective of the question. And we just say briefly that it is supported. Okay, so that would be it for this whole question. So you what might be confusing here to most people is the fact that we use this instead of the actual sigma. So we need to do 7.4 divided by 7.4 squared divided by 50, and then you square root that. Or 7.4 divided by root 50 we'll also do, and that is your new standard deviation to test the to use to calculate the probability here. All right, and that is that's it for part D. Let's have a look at the next question I got for this topic from June 2023. Yeah. Number 6, a medical researcher is studying the number of hours T a patient stays in the hospital following a particular operation. The histogram on the page opposite summarizes the results for the random sample of 90 patients. Okay, we're going to use the histogram to estimate the probability between 10 to 30. Okay, let's go check the histogram. So 10 to 30, so 10 is here, 30 is here, right? Because the histogram typically has the y-axis to be frequency density, right? And the x-axis is just the data. So we got to be careful there. We just be reminded that the frequency, right, is the frequency density times the class width. Now, what if we don't want the frequency of a single bar? We want part of it, right? We can use the same concept. So, for example, for the bar from whatever this is, I don't know, 7 to here, yeah. This is from 7 and a bit to 10 and a bit. This is a single bar, but what if you just want from 10? Well, you can just find the width from 10 to whatever this is and times the height. Then you're going to get the number of patients in this region alone. And then you find the other areas up until, 30. Okay? So we're going to be careful with the scale here. And, for the sake of explaining here, let me just copy the diagram first. Yeah? And then I'm going to put it here in my screen. Here we go. Okay, right. So let's see. Well, we want probability, right, of x greater than 10 but less than 30. So let's mark something here. So 10 is here, right? And 30 is here. Basically, we want all the areas, right? all the areas highlighted there. But because you want to find the probability, right? It asks you the probability here. That means you need to know the total patients, which is 90. And we do the number we get from this area divided by 90. That's the steps there. Okay, so let's see about the area here. Seems like this is 2.5. Okay, so one tiny square is for 0.5, right? Because this is 1 here, 2, 3, 4, 5. Yeah, so one tiny square is just 1. So let me just delete something out first so that I can see clearly. Yep. So this is 1 and 2. So the width of that cylinder rectangle there is 2, and the height, yeah, this height here is it the same here? So 1, 2, 3, no, it's actually 10. Yeah, this is 10, sorry, in 0.1. So that is the height of 4.2, right? Yeah, so the first one will be, just gonna write down here first, this bit of area is 2 times 4.2. Okay, that's 2 times 4.2. You gotta be careful because they might have different scales, like the division of the scale might be different for the x and the y axis. And then, okay, we got that one fine, and this whole bar is just 4 times. The width is 1, 2, 3, 4, yeah, so that's 16, that's easy. This bar here is 1, 2, 3, 4, yeah, also 4 times. The height is 3.5 instead. And just this bit of the bar, yeah, the whole bar is too much. We just want up to 30. So from 20 to 30, yeah, that's just 10, right? If you can see from the scale, and the boundaries are clear like that, they're on the markers, then it's clear that you can subtract. So this is 10 for the width, and then the height is just 1. Okay, and we're gonna add this up. So this is 8.4, this is 13.5, I believe. Nope, it's not, it's 14. Yeah, and then this is 10. Okay, so you add them up there, you're gonna get the value for the numerator. Yeah, and then you divide by 90 for that, right? Let me check everything. I think I'm happy with that. Then we're going to use a calculator, which is not that one. It's actually this. Fraction, 8.4 plus 16 plus 14 plus 10, no, 10, 90 here. So that's 0.538, 3 significant figures. Okay, I got that one. Part B, for these 90 patients, the time spent in hospital following the operation had a mean of 14.9 hours, a standard deviation of 9.3 hours. Thomas suggests that T can be modeled as normal distribution. B, with reference to the histogram, state giving a reason whether or not Thomas' model could be suitable. Well, we got to use the histogram, and bear in mind that normal distribution, the key property is symmetry. It is symmetrical, right? And we know that histogram looks not so symmetrical here. Okay, so a very good normal distribution should be such that like the outline of the top, like the top features, like the tops of the bars should be so that you have an outline just like a bell curve. So the bell curve, the histogram might have bars like this. Yeah, left and right symmetrical, where you have in the middle taller up. But it's not the case here. Rather, what it's showing you is more like, if I redraw them quickly here. So it's more like that. And this is actually positively skewed, right? Positively skewed. Okay? So this is positively skewed. Positive skewness, yeah? Okay? So having looked at the histogram, we say that the data is positively skewed. Okay, if you are certain that it is positively skewed, you should say. If you don't know and they don't look symmetrical, so you just say they're skewed, the data is skewed, and then you just say not suitable, right? For normal distribution. Okay. Yeah, that's it. Part C, Xiang suggests that the frequency polygon based on this histogram could be modeled by the curve with equation that. Wow, that looks like, x e to the minus x with a constant here, okay. X is measured in tens of hours. We gotta be careful there. K is a constant. C, use algebraic integration to show. Okay, so this is a mix to a little bit of pure math here. So we're gonna get that done quickly, yeah. So just by parts integration, I think, yeah. So we're gonna show this. So if I use that as u and this is dv, so uv, so v would just be minus e to the minus x, right? If you integrate e to the minus x, you get minus e to the minus x, so that's just u and v, yeah, minus e to the minus x. So I put the minus in front. Minus integral du, which is 1, and then v, which is also minus e to the minus x, and minus times minus, we get a plus here, dx. So that's minus x e to the minus x, and then I integrate that, I get a minus again. Right, okay, so we need to put the bounds to be 0 and n, yeah, so we don't have to do the constant c there. And then we're going to put minus n e to the minus n minus e to the minus n. And then when I put 0 in here, it's going to vanish. But when I put 0 here, I can still get something. So that's minus e to the 0, which is 1. So this will become a positive. So we put 1 here in the front, like they have there. And then this is going to be minus, and you pull minus n out, you get e to the minus n plus 1. No. You pull e to the minus n out, sorry. You pull e to the minus n out, you get n plus 1 instead, which is what they have there. Well, it's just different order of writing, but that should be fine. Okay, so as required here for C. Part D, show that Xiangs model k equals 99 to the nearest integer. Okay, for Xiangs model, so basically we just proved that k equals 99. So we have integral 0. Now, because we still have to stick with the units here, because x is in tens of hours, so this will be 4, right? And then this is the same thing. We put k x e to the minus x. We are integrating that, yeah, integrating that whole histogram. Dx, this will be put equal to 90, not 9. All right. So, okay, because we already know that the integral of x times e to the minus x is just this guy, right? Just this guy. So if we put k outside, yeah, I'm just going to write that first. That whole thing is just actually 1 minus, because we put the upper bound n to be 4, so this is going to be 4 plus 1, e to the minus 4, yeah? And then equals, sorry, this is 90, right? And we're going to find the value of k, yeah? So k equals all that. We're going to use a calculator to see if we get close to 99, right? So let's bring my calculator to calculate that. So that's 90 over 1 minus 4 plus 1 is 5, e to the minus 4. Okay, yeah, that's 99. So that's just 99.072 blah, blah, blah. I'm going to put that as 99. Okay, so that's done for part D. And then part E, estimate probability between 10 to 30 using Thomas's model, which is T normal distribution here. Okay, so we're just going to calculate the probability just by the normal distribution way. And you can do this by putting in the graphing calculator, normal distribution. Lower is 10, upper is 30, mean is 14.9, and standard deviation is 9.3. But I'm going to use a Desmos calculator here. Okay, so function, and then I go normal distribution here. So mean is 14.9, standard deviation is 9.3, and then we're going to do area, the inner area, because we want from left to right. So that's 10, and that one is 30. Okay, so that is just, let me write down the value first, 0.64863 blah blah blah. I'm just going to round that to 649. All right, so that's the probability of 10 to t to 30. Okay, part II. Xiangs curve with equation y equals 99x e to the minus x, and the answer to part C. Alright, so we're going to find still the same thing, probability from 10 to 30, but now using Xiangs curve, right? Bear in mind that we have a 99 here as well. So to use the answer to part C, which is the result of the integration here, so this will give us the number of patients from 0 to n. Tens of hours, right? So for example, if we, well, to find the probability of this, yeah, we need to maybe do t less than 30 minus p of t less than 10, because we want to define the inner area there, yeah. But for p less than 30, we're going to use that integral in part C. How do we do that? Well, if we just do n minus, well, 30 here, when using Xiangs curve, we need to do 3. So the upper limit is 3 instead, because don't forget x is in tens of hours, not hours, right? So this is 3 plus 1 e to the minus 3. Yeah? But this is only the result of this integral without the k. So if we put the k here, and remember when we do the integration, we're gonna also have a k outside, and k now is 99, so we're gonna have to put 99 here as well. Okay, this will give you the number of patients less than 30, right? 30 hours of waiting time. And we do the same for, sorry, this is 99. We do the same for the other one, which is also 1 minus, well, this time we're gonna do x equals 1, sorry, n equals 1 for the upper limit. So this is just 1 plus 1 e to the minus 1. Yeah, so that will be the number of people from 10 hours to 30 hours. But because we want to find the probability, we got to divide all this by 90. Yeah, that will give you the answer there. So we're just going to plug everything in a calculator. I'm just going to do fraction and 99 outside everything. And then if we just factorize 99 out, we can see that the 1 here will cancel with the 1 here. And we only have this term being a plus, right? If you try to do the math there. So it's 2 e to the minus 1. And then this is a minus. The other term is 4 e to the minus 3, yeah? Okay, pulling 99 out, the 1 cancel, we only got that left, all divided by 90. Okay, so that's the answer there, 0.590, isn't it? Yeah, that's the answer there for part EII. Now let's have a look at part F. The researcher decides to use Xiangs curve to model probability of A less than T less than P less than B. Right. State one limitation of Xiangs model. Well, if you think about the reality of this situation here, the patients waiting in line for their treatment, yeah, or just to see the doctor. Well, Xiangs model is, just putting the whole situation to 0 to 4, meaning that the maximum number of hours is just 40 hours. right? Because don't forget x is in tens of hours, right? Yeah. So you stay in a hospital. You can stay overnight or 2 nights or 3 nights. What if things go wrong? By putting the upper limit here, 40 hours, to the reality there, that might distort the situation. Because what if some or even a few people have to stay longer than 40 hours? Because, things go wrong, they have some side effects, they get sick after the operation, whatever. That's gonna increase the probability of other hours greater than 40 in the model. So if you limit to only 0 to 40, 0 is fine, there's nothing wrong with that because you can't have less than 0. But to limit it to 40 hours, that's gonna ignore other cases when they actually go to greater than 40 hours. So if we put this into the context of reality here, Xiangs model calculation here will just narrow down to just those people having to stay just within 40 hours. So this might be an like an underestimate, because you don't account for the whole thing. Okay, and that is the limitation here to the reality, right? So some patients might have to stay longer than 40 hours. So this model, so Xiangs model, does not account for those cases, right? And that's it. That's the whole thing for this question. Now let's have a look at the next topic, hypothesis testing. Yeah, this topic may appear hard for some people, right? But okay for other people. But let's see. The first question I have for you is October 2022. Okay. Number 4, a dentist knows from past records that 10% of customers arrive late for their appointment. You see, usually hypothesis testing kind of question will mix with other chapters like correlation and binomial distribution or even normal distribution, right? So we're going to have to do some questions overlapping on other topics first before we get to the actual hypothesis testing. And actually, there were already some questions that we needed to do hypothesis testing as well, right? But anyway, a new manager believes that there has been a change in the proportion of customers who arrive late for their appointment. A change, right? A random sample of 50 of dentist's customers is taken. Write down the null hypothesis, right? So null hypothesis, well, it's just H naught. Okay, and we gotta have a look here. This is binomial because it's 10% arriving late, so 90% not arriving late, right? So it's just 2 outcomes here. That means we're gonna do P instead of mu, right? So P equals 0.1. But for the alternative hypothesis, it's just P not equal to 0.1 because there is a change. He believes there's only been a change, not a decrease, not an increase. So this is two-tailed test, right? Okay, that's part A done. Part B, using 5% level of significance, find the critical region. Now this might be confusing for some students. Okay, I have experience having to teach students and they get confused about critical region here, but let's see. Okay, so it's good for your revision as well. So we're gonna use each tail, 0.025. Okay, that's 2.5%. So if I may draw the distribution, and this is not meant to be a bell curve, it's just binomial, and binomial is also kind of like, in a way symmetrical, but not to be confused with normal here. Anyway, so we want this 0.025 and this 0.025, right? So we are finding x1 and x2. So the value less than or equal x1 will be a critical region for the left tail, and the other value x2, so from x greater than equal x2 will be another critical region for the right tail. So the critical region will be, it will have two areas here. Okay, so we expect to get less than or equal x1 and greater than or equal x2. Okay, now how do we do that? Of course, we're going to use binomial what's that, 50 and 0.1. Okay, so the best way is to use the table. Yeah, we should use the table here. I'm just going to do x modeled as that. Okay, let's have a look at the formula sheet I have here. So this is the Pearson Edexcel level 3 blah 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 for all the math modules, and then we're gonna look at the binomial table, which is here. We are lucky that n is just 50. That's the maximum n we can get. Yeah, okay, so we're gonna focus on this. Okay, now we want to look at the value. Okay, let's do the left tail first. So we are looking at x less than some value where the probability starts to be at first smaller than 0.025. Okay, so let's have a look. P is 10 in this case. Yeah, P is 0.1. I mean, yeah, and then this one is too small, so we're gonna find the first one that starts being smaller than 0.025. And it seems like if we do P of x less than or equal 1, we're gonna get already greater than 0.025. So we gotta write two values here. Yeah, so I'm gonna write P of x less than equal 0, which is x equals 0 basically, 0.0052. Yeah, for this one here, and the other one here, yeah, P of x less than equal 1 equals 0.0338. Right? Now we stop here because if we keep going, the probability will only increase. Right? We want just the one that starts to be smaller than 0.025. So this is our candidate here, because the other one is greater. But we need to write both because we need to show the one that starts to be smaller, right? Because if you don't write like at in between the two values, and you pick the one, you choose the one that starts being smaller, they're probably not going to give you mark here, because I mean look, if there were more values up here, then all of them will be smaller and smaller. So you could have picked any one of those if you don't show here that, okay, after this one, it starts being bigger now, so that's why you choose this one. All right? That's just the way we do it. So here I say x1 equals x1 equals 0. That's the first critical region. The next bit is a little trickier. Okay? So this area here will be x greater than equal x2. Well, that means when we look at the table here, it's going to be the opposite. So actually, it's the opposite area where when we go one less, because this is discrete, remember, it's binomial. So we got to find the probability of x less than equals something, yeah, which is actually just x2 minus 1, because we got to go one less. Remember, if we flip to the other side, and let's see. So we need to find the one that gives the area of at least 0.975, right? Yeah, because that's 1 minus 0.025, so that's 97.5%. So if we look down, the ones that near 0.975 is this one. That's already bigger. So I gotta choose these two and discuss, right? So that one is, I'm just gonna write P of x less than 8 gives me 0.9421. Well, that's not quite the one we want yet, because it's not 0.975 yet. And if you go one more, it's going to be that, right? So it's going to give you now 0.0975. So that is already in the critical region. But you got to be careful here, because this number 9 here will be the same as x minus 2. Because remember, we want the left tail, the left area here, to be at least 0.975. And this is already okay. But don't forget that the critical region will have to be one more and to the right, because we do discrete here. That means this is only x2 minus 1, right? So x2 minus 1 is just 9. That means x2 is going to be 10. Okay, you got to go one more to the right. Okay, so that means the critical region, yeah, is just the thing we want here, critical region. Okay, is going to be x equals 0 or x greater than equal 10. All right, make sure you understand this, yeah, about the critical region here. Okay, next, part C. Find the actual level of significance of the test based on your critical region from part B. Well, basically, we just find the actual percentage area here on this one and this one. So this one we got 0 here, this one we got 10 there. So we're just going to add up these two areas, basically. Okay, so for the 0, it was 0.0052, right? And for the 10, well, we can do 1 minus this, because 1 p of x greater equal 10 will be 1 minus p of x less than equal 9, right? So that's 1 minus 0.9755. Yeah, so that's 0.0245, right? And we're going to add that to this. Yeah, so let me put in order there, in a logical order. Okay. And that's the actual level of significance, guys. I'm going to use a calculator. Yeah. So that's 0.2502. Okay? Is that right? Yeah. Oh, no, it's not. This is 0.0245. Yeah. So that should be 0.0297 instead. Okay? So that's actually 2.97%, the actual level of significance. Yeah, for the critical region. Part D, the manager observes that 15 out of 50 customers arrived late for their appointment. D, with reference to part B, comment on the manager's belief, right? So the manager belief was that there is a change in the proportion of customers arriving late, right? And 15 customers arriving late out of 50 is the same number of trials, so we are fine. 50, if we look at our critical region in the earlier part, it is greater, quite greater than 10. That's like far greater than 10, like 50% greater than 10, yeah? So we say 50 is greater than 10, so in the critical region, okay? So there is enough evidence to suggest that there is a change in the proportion of customers arriving late. Therefore, right, the manager's belief is supported, basically, just right like that. Yeah, just like that, supported. Okay, you know what I mean there. Yeah, and that's it for this one. Let's have a look at the next one from June 2019. This is also interesting. because as you can see, there are logs there. Okay, Barbara is investigating the relationship between average income GDP per capita, X US dollars, and average annual carbon dioxide CO2 emissions, Y tons for different countries. She takes a random sample of 24 countries and finds the product moment correlation. So this one is a good blend between hypothesis testing and correlation, right? Because as you can see, hypothesis testing is not a single separate question. It mixes with other topics, and because there haven't quite been any hypothesis correlation questions in this walkthrough, so that's why I put it here as well. But usually this question is not hard. I mean, the correlation topic isn't hard, right? Usually, but this one is a good mix. So let's go. Okay, she takes a random sample 24, and the correlation, product moment correlation coefficient is 0.446. State your hypothesis clearly, test at 5% level of significance whether or not the product moment correlation coefficient for all countries is greater than 0. Okay, yeah, so for product moment correlation, it's quite straightforward. So you just write the row here, which is the R basically, but we write row is equal 0, and H1 is just greater than 0. That's it, because we want to test whether there is a evidence for it being greater than 0 here. So the assumption is to be, is to put it at 0 first, and the null hypothesis is to say that it's greater than 0 because there's a positive correlation here. All right, and then so n is 24 here, right? And the level of significance is 5%. Okay, so and this is just one tail, right? Yeah, usually. So we look at the formula sheet. Let me get that. Okay, so we're gonna look at the critical value for correlation. So 5%, yeah, here we look at the product moment coefficient, not the Spearman. That's further statistics, I believe. And we look down here, the sample size is 24. So 24 is here. We're going to look at this row. We want 0.05. So the critical value, yeah. So the critical value is 0.3438. Now, if you were testing negative correlation, you would have just put that as negative 0.3438 instead, the critical value, I mean. Okay, now, so here we got our critical value. We're just going to go back to the question paper. There we go. And as we can see, right, the calculated product moment correlation is greater than this, right? So 0.446 greater than the critical value, right? So we reject the null because it's significant now, right? And say that there is evidence to support that, the PMCC for all countries, is greater than 0. You know what I mean here. Just write that. It's a pattern. You need to just write that down to get the mark, right? Okay, and that's it for part A. Straightforward. Just take this as a revision maybe. It's not too hard. Next, Barbara believes that the nonlinear model would be a better fit to the data. She codes the data using the coding. Okay, you have coding, logarithmic coding here, not linear. Okay, so she is changing from m, which is the m as log base 10 of x. So x was the average income, changing it to m, and c was the carbon emission. Sorry, y was the carbon emission and changing it to c, and obtains the model that the product moment correlation coefficient between c and m is found to be that, right? 0.882. Explain how this value supports Barbara's belief, right? Well, she believes that the nonlinear would be a better fit. Okay, and so if you look at this equation here, yeah, this one, I mean, if you just put log base x, log base 10 of x and log base 10 of y back into that equation, what do we have? We have log base 10 of y equals minus 1.82 plus log plus 0.89 times log base 10 of x, right? I mean, look, if you plot like log base 10 of y against log base 10 of x, according to this model, of course, it's a linear equation, so you're going to get a linear equation. But this will have come from the scatter. So imagine she is plotting log base 10 of y as a scatter against log base 10 of x, and she probably got something like that. And that would have been the line of best fit, let's say, okay, maybe a little lower because it's a minus here. And do you see that as the product moment correlation is quite good, this is a good positive correlation. So that means as value is getting closer to 1 here, this regression model will have come from, the scattered data that is closer to a linear relationship between log base 10 of y and log base 10 of x. Okay? So we say that 0.882 is close to 1. So indicating a good positive correlation. Yeah. Therefore, log base 10 of y versus log base 10 of x plot is close to a straight line. Like that. Yeah, that's how we say it. All right. Now, next part C. Show that the relationship between y and x can be written as that. Well, this is probably pure math, right? So part C, we already got earlier that log base 10 of y equals minus 1.82 plus 0.89 times log base 10 of x. Okay? And we're just gonna maybe, you can do, so you can just rearrange. If you don't write the 10, it's still gonna mean base 10, right? So I'm just gonna ignore that for now, too much writing. And I'm gonna put this as log x to the power of 0.89 using a log property. And of course, you can, raise to this power, raise the two sides as powers of 10. So we have 10 to the log base 10 of y equals 10 to the power, of minus 1.82 plus log base 10 of x to the power of 0.89. Okay? Of course, using the log property, that will become y. And here we can split into these two terms. Yeah. Yeah, so we have 10 to the minus 1.82, right? So we got to estimate that constant. 10 to the minus 1.82 is 0.0151, yeah? And that is just, x to the power, because using a log property again, that's going to just bring the x power down as that. Okay? So, yeah, we got it. So A is 0.0151 and N is just that. Okay, so, I could write A equals 0.0151 and N is, was it N? Yeah, that looks like an N. Oh, yeah, it's N, 0.989. Okay, so that's it for this one. Now, next one is again June 2024. So again, I would refer to the walkthrough that I already did on this whole paper, June 2024. You should check out that whole paper. It's a very good paper. As you can see, I have mentioned this paper on a couple of questions on 2 or 3 topics already, because generally it's a good paper. So definitely check it out. And that would be the third question here I have for this topic, which is good. All right. And that was it, guys. I hope that was all useful. And again, don't forget to check June 2024 walkthrough, and also the hard questions on mechanics as well. So that's going to definitely be useful. And stay tuned, because the large data set is also coming up, right? Or if you already seen it, it's cool. Okay? Please like or subscribe, or do both if you love me. And I'll see you in the next video. Bye.